Maybe, so let us move on to the next talk, which will be given by Colin Christopher, and that is Instrumenting the Moon as a Spherical Gravitational Wave Detector. So this talk is quite relevant to this first talk, I guess. So I guess, Collins, you have 15 minutes. I will warn you when you have 2 minutes left.
Okay, thanks. Can you bring the slides up?
And excellent.
Okay, so yes, I guess in a way this is a sort of a continuation of the previous talk, with I guess focusing on a slightly different variant of the same detector. So yeah, just to introduce it. So I guess a lot of this has been covered. So the moon is seismically very quiet, and also has I guess lower gravity gradient noise at lower frequency than on the Earth. We don't yet know exactly how quiet, so that's essentially we can put an upper limit on it, but it would be good as an intermediate step to make some more sensitive seismic measurements. Okay, next slide, please. And yeah, this is just showing again some moonquakes, which are follow. Well, they've been categorized quite well, but there are large gaps in between them where we essentially see no observable noise. Next slide, please. Okay, and this is essentially, so we're suggesting a slightly different configuration than Jan. We hadn't kind of planned to use necessarily go into a crater. I think we will just try and cool the experiments with standard heat shielding. We're proposing an isosahedral arrangement of accelerometers, so there will be 6 of them, and using this we can get essentially uniform and uniform and isotropic response to signals. And so this is a configuration that has been used previously in a ground-based resonance detector, and so we're scaling that up by a factor of roughly 1 million in terms of length and 10 to the 18 in terms of mass. Next slide, please. And finally, so this is the sensor that we're proposing. In some ways, simpler, but with a few different features from the one Jan was describing. So it's essentially just a pendulum, a mass suspended. We would aim to have a high mass and low temperature to reduce the thermal noise. For the displacement sensor, we propose a capacitance bridge sensor coupled to amplified by a DC squid, which gives I think it looks like, I guess, similar sensitivity at around 1 hertz or 0.1 hertz, perhaps better low frequency sensitivity. So a key feature we also use using the fact that it's cryogenic anyway is we have a superconducting anti-spring system, which allows us to adjust the resonant frequency of the test mass. And so we would hope to, if we start with a resonant frequency of 0.1 hertz, we should be able to achieve a resonant frequency below 1 millihertz, so below the fundamental mode of the moon, and we think as low as 0.1 millihertz, which will then improve our displacement sensitivity at those frequencies. So, next slide, please. Yeah, this is just the same thing. So showing our displacement sensitivity curve. So yeah, it's kind of, well, at high frequency, we get a peak sensitivity of 10 to the minus 20 meters per hertz. We hit the target of 10 to the minus 15 meters per hertz at 0.1 hertz. Next slide, please. And this is just again showing the different detector configurations and the response to different direction signals. So just showing that with an isosahedral configuration, it's essentially equivalent to a sphere. So, next slide, please. Okay, and then this is, I guess, another component in the analysis in terms of determining strain sensitivity. So we have one thing is the sensitivity of our inertial sensor to ground motion. The other component is the ground motion we see from a incoming gravitational wave signal. And so to determine that, essentially, well, to determine that fully, we need to know a lot about the structure of the moon, but we can, in some ranges, we can kind of make simple statements. So our frequencies below the fundamental mode of the moon, we will see the essentially the moon will be rigid. Its response will fall off as the frequency squared, and so whereas a inertial sensor, an ideal inertial sensor such as a massive free fall, would respond to the gravitational wave at all frequencies. At very high frequency, the ground and the test mass of the inertial sensor will both co-move with the gravitational wave, and in between, we see all the elastic eigenmodes of the moon, and so the response is kind of a weighted sum over all those transfer functions. The weighting coefficients we find by just integrating the force exerted by the gravitational wave over the moon. And so, yeah, to start with, we treated the moon as a isotropic resonant detector, as a uniform isotropic sphere. Okay, next slide, please. And this is the predicted sensitivity. So at low frequency, this is using, if we can tune the mass to a low enough resonant frequency, then we can get close to LISA's sensitivity. It's within an order of magnitude at frequencies below below 1 millihertz. And then we see resonant enhancement at the peaks. Now we don't know the exact frequency or Q of those peaks of the fundamental and the lowest orders of the moon, and so this is a qualitative picture. The resonant enhancement would be proportional to the Q, and so, but either side of that, I guess the signal just below and just above a peak would be just determined by the overlap integrals, which we're less uncertain about. And then you see on the right, I guess this is where it kind of gets more complicated. We get lots of modes of the moon excited, and to really be confident in that, we'd have to know a bit more about the structure of the moon. But it certainly seems that we can get well, more sensitive than LISA so it looks like we can have some useful sensitivity in the mid-frequency range, so 0.1 to a few hertz. So it could function to bridge the gap between LISA and LIGO. Next slide, please. Okay, and this is essentially ongoing work that we kind of need to do, is to just look at the effects of having the moon, well, give them a more realistic model of the moon, so treat it not as a uniform sphere, but put in the different the core and the different layers. And finally, we can also then look at the inverse problem. So given this extremely sensitive instrument, what could we learn about the internal structure of the moon? And so this is, I guess, something we need to consult with lunar geodesists to really say a bit more about. Next slide, please. Okay, so almost finally, so just some of the major error sources. As we said, there's still some scientific noise, and we would like to measure that. We want to use a cryocooler to allow continuous cryogenic operation, and so we need to do that without incorporate that without adding noise. The gravity gradient noise from thermal effects we want to minimize. There's electrostatic and magnetic noise sources that will interact with the instrument. I guess we can add to that as well. Temperature fluctuations we need to minimize for the operation of the instrument. Next slide, please. Okay, so this is, I guess, the final slide. So the technical developments required. So we need to develop the vibration-free cryocooler, and this is something that we're working on for a NASA project for a gravity gradiometer, which would be satellite based. So I think making something ground or moon-based makes things easier in some ways. We need to, I guess, develop the low noise superconducting accelerometer so that we can actually reach this sensitivity. So we are developing some key components, the high Q and the spring anti-spring systems for that. And then I guess the data analysis problem of essentially it's no longer a nice, neat, linear, strange signal like LIGO, or at least it will be. We've got these resonant modes, and so extracting the data from that will be something we need to have a plan for. So yeah, that's it. Thanks for yeah, any questions?
Chris, excellent. Thank you very much. Are there any questions? There is a question or comment by Marshall Eubanks. It sounds like a lot like an update from Weber's experiment on Apollo 17, which is, yeah, I think it's interesting. Any comment on that, Chris?
I'm not familiar with it. I don't know.
See, you are planning to have instruments on the near side because of you don't need to do sort of, I guess, far side relay satellite. On the near side, thermal environment may be quite challenging, right? Because it fluctuates from by more than 200 degrees, and essentially coupling to the regolith, I think it needs to be addressed very significantly. And I think maybe Ho-Jan can comment on that.
If you go down 30 centimeters, it doesn't fluctuate nearly so much. The depths you're talking about, Barrett.
I can comment on this deployment of this ICA, the Taiga arrangement. Basically, because of the the symmetry, you can be anywhere, any hemisphere of the moon. It can be on the opposite side, but the concern is the power. Obviously, we have to solve the power problem. So,
absolutely.
Yeah. So if you have actually 12 of them, then 6 of them will see the sun all the time. So, but yeah. So anyway, any 6 of them on hemisphere will do the job. So Weber only had one gravimeter, which is not enough to distinguish the quadrupole mode from other modes. But by having this 6 of them, we can reject non-gravitational waves. This is like anti-coincidence. Okay.
Absolutely. How do you synchronize those instruments? Do you have to, or how? And if you do, how do you do this?
Okay, so I have been thinking about how to not only synchronize but calibrate and so on. So we have been thinking about this. Detecting horizontal part is easier, but I have been thinking that I have to detect the vertical as well. If you detect the vertical, then monopole excitation, which is not gravitational. If the moon or anything gives us a monopole excitation, and then those 6 the accelerometer should have more or less. There is some error because moon is not perfect sphere, but then more or less it's breathing. So you can synchronize and calibrate. So to do the very important science to test the general relativity, whether monopole wave exists, that's always a remaining question. So we like to probably measure the vertical as well as horizontal.
Excellent. Thank you very much. So maybe a good discussion. So maybe on this note, we should move on to the next presentation. And thank you, Chris, and thank you, Ho-Jan, on that. So next presentation.
Is Jan back? Can we hear the rest of the Jan's talk?
Jan, would you like to summarize maybe in like last couple slides of your presentation?
Yeah, in fact, so there was a sensitivity slide. I don't know where I actually dropped out. Maybe we can have this also later in the discussion. But I'm just to say that scientifically, it is a very, very interesting concept because it's also possible to close observational gap that is left between the ground-based detectors on Earth, also of the future, and spaceborne detectors like LISA. So the lunar detectors can be right in between and also towards lower frequencies, overlapping a little bit with LISA as well. So I think scientifically, this is a very interesting observation band as well, which I wanted to point out on my last slide. Yeah.
Excellent. Have you thought about, I guess it's a similar question I asked Chris and Ho-Jan. Have you thought about how will you couple your instruments to the regolith in a permanently shadowed crater? because it will be warm, and as it is warm as time goes by, the instrument will sink, and so will potentially there will be some signatures. But I think they will be easy to couple. Have you thought about this?
No, we have not thought about the coupling to the regolith yet. No.
Okay, all right.
Actually, yes. Yeah, when I first presented this talk in 2004 at Caltech, Jan Harms and then Kip Thorne wrote about I think the lunar regolith damping and so on. So we don't know how much those things affect the gravitational wave detection.
Thank you very much, Jan, and thank you, Jan, for coming back and summarizing your talk for us. So we should move on.